Okay, hello. All right, this is an additional problem I want to work through from section 4.4. It's dealing with, got a function that, let's go ahead and call this up. We're going to take the first derivative test, use it, take the second derivative test, use it, and make determinations of different aspects of the function. So what I'm going to do right now is go back to the iPad and show, here's the function. F of x equals x to the third minus 6x squared plus 9x plus 30. And the assignment is to find any local extrema, and that rings the bell of the first derivative test, and B, then determine where f of x is concave up and where it is concave down. So we'll take the first derivative and get the solution to that, set it equal to 0, right? 3x squared minus 12x plus 9, which is equal to 3 times x squared minus 4x plus 3, which is equal to 3x minus 3 and x minus 1. All right, so we can see kind of quickly that x minus 1 equals, we set this equal to 0 now. And that's going to happen where x minus 1 equals 0, which is x equals 1, and x minus 3 equals 0, that is x equals 3. So using the first derivative test, we can see that our critical values are 1 and 3. And if I pick a value to the left, 0, a number in between, say 2, and the number to the right, 4, then I'm going to check these 3 in the derivative function because I want to see where the slope is increasing and where it's decreasing, and see if we have local min and local max. So again, we can look at the function itself and remember what the shape is. It's a cubic, and it's a cubic function, and it's got these extra little ditties on there. So that's evidence that it's going to be looking like this. You know, that's the general idea. So it looks like 1 might be a max. X equals 1 was where the max occurs, and x equals 3 is where the min is going to be occurring. So let's take a look at that now. We plug in the 0 into the derivative function. And if you notice, you've got a factored form here, but that means if you plug 0 in there, you got to do 2 multiplications. If you plug it into the original function here, you plug in 0, you get f prime of 0 equals 0 plus 9 equals 9. So we get plus 9, which means it's positive here, which means it's going in that direction. And if you look at 2, you end up with f prime of 2 equals what? So this one I'm going to break down into the factored form here. And I end up with 3 times minus 1 times 1. That looks like minus 3. So we end up with minus 3, so that's minus, which means it's looking like this. So we got a max up here at x equals 1. Yeah. And then we plug in 4 into this puppy. This is the first derivative test again to verify if it's a local max or local min. We end up with 3 times 4 minus 3 times 4 minus 1, which is 3 times 1 times 3, which is 9, which is positive. And that means it's looking like that. So we've got a local min here at 3. So, and notice, so we got a slope is negative in between. It's decreasing in between 1 and 3. It's increasing on the left side and increasing again on the right side. So what we can do now about concavity, remember the situation of what we're trying to do is make a determination. What we can do is we can plug in the actual critical number itself, the critical value, and plug it into the function and verify whether it's concave down or concave up at that point. So if we find the second derivative now, the first derivative is equal to, let's go to the whole thing, 3x squared minus 12x plus 9. The second derivative then is equal to the derivative of that, which is 6x minus 12, which is 6 times x minus 2. So it looks like the second derivative, it will be equal to 0 at x minus 2 equals 0 at x equals 2. So at x equals 2 is where there will be a possible point of inflection where it's changing from concave down to concave up. So if you notice, if we plug the value in of the function, the critical value, f double prime, the second derivative, take the second derivative at this point, it'll tell you whether it's concave up or concave down. Second derivative at x equals 1, you get 6 times negative 1 is negative 6. So at 1, you get the idea that it's concave down because it's negative, less than 0. And the second derivative at what? What's the other critical point? 3. We end up with 6 times 3 minus 2, which is 6 times 1, which is 6, which is positive, which is concave up. And that makes sense. At 3, it is concave up. So we end up with a graph that looks like concave down here at 1, at x equals 1, and concave up here at x equals 3. And so you get the general focus of what the graph looks like. And in general, yeah, so, and at the point right here at x equals 2, the halfway point in between, we end up with where it's changing from, we get 0 there. Notice the second derivative is equal to 0 there. When you plug in 2. And that's evidence that there's a possible inflection point. And if you go to the right, it is concave up. And you go to the left, it's concave down. That's evidence that that is an inflection point at x equals 2. So, in the notation now, find any local extrema. The extrema are occurring at f equals 1. So we plug in 1 and figure out what the value at 1 is. We get, this is into the original function. Let's go f of x. Let me write that down. We get x to the third minus 6x squared plus 9x plus 30. And what I'm doing is I'm finding the actual values of the extrema at 1 and at 3. We get 1 minus 6 plus 9 plus 30. Is it 30? Yeah, plus 30. And that's 40 minus 30. 40 minus 6 is 34. So the coordinates are 134, 134. And that's a local extrema. And then at f of 3, we get the other, which is going to be the local min. So this is the local max. This is the answer to part A. And the 3, we get 3 cubed minus 6, 3 squared plus 9 times 3 plus 30, which is equal to 27 minus 9 times 6, which is 54, plus 27 plus 30. So this gives me 54 minus 54 is 0. That's equal to 30 there. So we end up with at 330 is a local min. That's that, that's that. And then we also get that it's, okay, now let's look at the notation. Let's look at the other circumstance here. Let me clear off a little bit of space over here. Okay, and see that, notice that, where is it, the interval where it's concave up and concave down. Notice the point of inflection is the point of change. So that means it'll start there, go to the right, and it's going to be concave up over this direction. So concave up, ready? So concave up on the interval starting at 2 and going over forever. So on 2 to positive infinity. And from 2 to the left, it's going to be concave down. Negative infinity up to 2. All right, so pardon me for having A under B. Here's the answer to part A, and here's the answer to part B, how we did it. Okay, hope you can practice that and get that squared away, get the logic of it, look through that. Again, the first derivative test totally gave us the extrema, and then taking the second derivative and using the logic of the situation, we were able to find where the function was concave up and where it was concave down. Okay, good. Good. We'll do a couple other problems in just a minute. So I'll get back with you, check in a little bit later, and practice this one. It's a good problem for just getting some basics out of a polynomial. All right. Wish you guys well, and I'll talk to you again soon.